We'll be starting a new topic in this lecture. We'll be continuing this topic via a series of lectures in probably the remaining part of the course. This is all related to power generation in some form of the other. There are many forms. We'll start with thermal combustion. Okay, so I'm giving this adjective thermal, because this can be differentiated from electrochemical combustion, which we will talk in a couple of lectures from now. So in this lecture, we'll be looking at enthalpy changes involved with thermal combustion. So in the previous lecture, we had looked at Joule-Thomson coefficient and involving isoenthalpic changes. So when these isoenthalpic changes occurs, there's a decrease in pressure when you throttle. However, the temperature can decrease, remain the same, or increase. So depending upon the temperature changes, the Joule-Thomson coefficient differs, is a measure of non-ideality of gases. And the way to analyze this is we had derived an expression for dH in such a process. Because it's isoenthalpic, dH is 0. From that, we can rationalize why some of the situation involve decrease in temperature, but some others do not involve decrease in temperature. We have defined something like an inversion line, and your inlet temperature has to be in a particular form so as to see a decrease in temperature. So we had seen this in the previous lecture. We had also looked at how to evaluate enthalpy changes in real gases as opposed to ideal gases. So to do this, we had imagined in a more elaborate process. For example, if you just want to evaluate enthalpy changes while you go from 1 to 2, instead of directly evaluating this, we imagine a different process where you go from state point 1 to a state point 1 star, which is an ideal gas state. Okay, so the temperature is changed along this ideal gas state, 1 star to 2 star, and from 2 star, you come back to this point 2. So there is an advantage in doing so, because we can use compressibility factor and develop similar charts for enthalpy changes, okay, by comparing how the real gas differs from an ideal gas. Okay, so we'll use such kind of procedures for enthalpy changes, and then develop certain charts involving excess enthalpy, okay, compared to how the real gas, enthalpy of the real gas differs from enthalpy of an ideal gas at the same temperature. And we'd use compressibility factor to tabulate such quantities. We have done a similar kind of computations for entropy changes too. However, the entropy changes is slightly more nuanced, because if you try to calculate enthalpy changes from A star to B star, this will involve singular values. So you avoided that and came up with a slightly more elaborate process to compute the enthalpy changes. But however, in the end, we also had something of a chart which talks about the entropy of a real gas as against the entropy of a ideal gas at the same temperature and pressure and so on. So all these things are tabulated in terms of charts. Okay, so X is enthalpy charts, X is entropy charts, and so on. So even in the case of entropy changes, instead of going from here to here, we had a process where you went from 1 star to a fictitious state, and then there is so that involves this entropy change, and then there is another fictitious state. This is a imagined state. Okay, so 1 star is a state which has the same temperature and pressure, but you imagine that to be an ideal gas. Okay, so how that computations were done was elaborated in the previous lecture. So please refer to that to know the details. Okay, so again, I emphasize that 1 star has the same temperature as state point 1, even though we are not indicated at the same temperature because of certain reason. Because the way we are presenting this is in terms of an in a TS plot. Okay, so there are certain complexities involved in representing 1 star. Moving ahead, we switch to a new topic involving energy. Okay, so Rick Smalley was a Nobel laureate who characterized C60, Buckminster-Fullerene molecule, using mass spectroscopy. And then towards the end of his career, last 10 years of his career or so, he spent a lot of time focused on a particular topic. Even though he was a chemist, he was a spectroscopist, the last 10 years of his, or last phase of his scientific career, he spent on a very important topic. So he wrote an important article in 2005 on what are the top 10 ventures that are required to save the world. Okay, so being from India, we always thought population is a big problem. Okay, so that's what we were told as kids. And then we talked about democracy, education, disease. This disease is very relevant now when we are in the midst of a COVID crisis. And then there is terrorism, war, poverty, environment, food, okay, food shortages, water. Okay, all these are all important. Okay, so population is amongst the 10, population least important, and then you progress. He had some way of measuring the extent of these problems, but the most important problem, he said, was energy. Okay, so energy is the most important problem right now. Okay, because if you imagine the number of people, if you have a measure of number of people in the world, everybody will want to have all these gadgets. Okay, every person will want to have a cell phone, a laptop, and the order of cars and TV sets and so on will be much more than what it is now. So from the demand point of view, not just supply point of view, from a demand point of view, there's going to be tremendous need for energy. Okay, and there is a direct correlation between prosperity. Here is per capita income on the y-axis, and per capita energy consumption. So as countries become prosperous, and every country will want to become prosperous, the people of the country will want to become prosperous, there is for sure an increase in energy utilization. Okay, so how are we going to manage this energy utilization is going to be the biggest challenge in this century. Okay, so this is going to be the dominant theme, engineering theme, as well as a theme for science and physics and chemistry. How do you capture energy and convert that into useful energy? Especially solar energy is available in abundance. So energy is not actually the real issue here. Energy capture, conversion, and storage is the more critical problem. Okay, so if you can, let's say, capture all the solar energy available, and or even a fraction, 10% of solar energy that falls on Earth, and you gainfully utilize it, there won't be any energy crisis. Okay, so energy per se is not the problem, but energy capture, conversion, and storage is the problem. So the form of energy we'll be addressing in this lecture is mostly about combustion. This is very different from other forms of energy. For example, there is nuclear energy, which we won't even talk about in this class, but it's very important. It is non-polluting, but there is a lot of issues involving safety because nuclear energy is highly dense fuel. Okay, so the power density, energy density of nuclear energy is very high. Okay, so that is its main advantage and main disadvantage too. Okay, so but if you compare the statistics, nuclear energy is quite safe. Okay, and what we will be talking about is mostly chemical energy. When there is rearrangement in chemical bonds, the favorable chemical bonds result in release in energy. That's what combustion is about. Okay, so you take hydrocarbon and combine with oxygen, you do oxidation basically. You form CO2, H2O, and so on. This favorable chemical rearrangement releases energy. So there are a lot of descriptive material that is available in the book. So I request you to go through that. There's no point in covering such issues in a class. It's sort of fairly elementary issues, but it's important that you at least go through them from your textbook. That's a reading assignment. So when there is favorable chemical rearrangement, the energy is released, and that is what is, that thermal energy released is what is used in combustion. When you burn petrol to run your car or to run a thermal power plant, you're talking about combustion. It's called different branches of engineering. You're referring to the same thing by different names. Okay, so in chemical engineering, we refer to it as high temperature oxidation and try to model it and design it and so on. In mechanical engineering, you may call it combustion, and you're thinking about thermal power plants. In aerospace engineering, you might be referring to it as propulsion following combustion. But all these underlying physico-chemical processes are one and the same. So in this lecture and the next lecture, we'll be looking into the thermodynamics of combustion, thermal combustion. So there are lots of, the elementary principles are fairly simple. Okay, you've seen this from high school chemistry. So you have to be just careful about referring to the states involving products and reactants. So when chemical molecules and products are present at 25 degrees centigrade and 1 atmosphere, this is an arbitrary reference state we take, and we call this as a reference state. We measure energy changes with respect to this state. For example, if you want to look at combustion, what we typically do is you take a combustible hydrocarbon. It need not be hydrocarbon, but that's what has been traditionally used. You started with a hydrocarbon which had a lot of carbon. Okay, if you look at historically, at this problem historically, you started with wood, okay, biomass, okay, cow dung, all these things are biomass and so on. And then you burnt it, right? And you burn not with pure oxygen, you typically burn in air atmosphere. So, okay, so air is oxygen and nitrogen. Theoretical air has a particular concentration of oxygen and nitrogen, and this results in carbon dioxide and H2O, and you hope that nitrogen has not reacted. That might not be so. You may also form NOx, and there might be sulfur in the air. Sulfur is there in the air, and that may generate SOx. These are environmental pollution, big problems, but those are not the focus of this class. We are just looking at an elementary thermodynamic modeling of combustion. So supposing the air that is coming in is at a standard state, and the fuel that is coming in is at the standard state, and the products that are being formed are also at standard state. So the energy changes involved is being released as heat. So the heat release, that is the enthalpy of products minus enthalpy of reactants. How do you specify these two quantities is what you have to pay attention to. So enthalpy of combustion is the number of is enthalpy of products minus enthalpy of reactants. So the enthalpy of products involves the number of molecules and enthalpy of each molecule involved in the product minus number of molecules of the reactants and enthalpy, standard enthalpy of each of the reactant. Okay, because here everything is in the standard state. Not only the reactants are in the standard state, products are also in the standard state. This might not be the case, so we'll see how do we address such issues in the next slide. But in this case, everything is in the standard state. So this is a simple enthalpy balance. Okay, so these quantities are available in tables. You should know how to read these tables appropriately, and from here we can calculate the enthalpy involved in combustion. For example, go through some of the solved problems and problems available in your textbook. So to also get a measure of what is the enthalpy of combustion we are talking about, how much energy is changed we are talking about. So there are energy changes mentioned in terms of kilojoules per mole, kilojoules per kg, and so on. And what is the kg we are referring to? Okay, so all these things are elementary things, but you should know how to specify this correctly, because these are have important consequence when you use the data in an industrial setting. Okay, in terms of practice, engineering practice, these are all of some importance. So as I said, most of the time we are not using the reactants and products in the standard state. They may not be available at 25 degrees centigrade and 1 atmospheric pressure. In that case, you specify enthalpy in a different manner. We will talk about the tabulated values in a minute, but enthalpy at any arbitrary temperature and pressure is what is referred here in the left-hand side. That is documented using two quantities. This is the enthalpy of formation of the standard state. I will explain this and contrast against this using these tables. So the enthalpy at an arbitrary temperature and pressure is obtained by enthalpy of formation. F refers to formation of that particular compound in its standard state. This not refers to standard state, plus there is enthalpy of, there is another enthalpy involved, which is also in standard state, but this is at 1 atmospheric pressure and 25 degrees centigrade. And this is the enthalpy of your particular compound at the temperature and pressure you are talking about. Okay, so this is again elaborated here. So for example, if you want to calculate at any arbitrary temperature and pressure, it involves this quantity, and then there is a reference quantity at a reference temperature and pressure. This can be standard state again. And then there is this quantity. So let me elaborate this using these tables. Okay, so here what we are talking about is enthalpy of formation in along this particular column. So enthalpy of formation of elements, okay, carbon, hydrogen are arbitrarily given value of 0, because this won't matter. You can, because we are going to be talking about changes in enthalpy. So this is some datum level. So if you say elements, carbon, it's easy. And what is the element? This element is present in the standard state, which is the solid state. Okay, so that is given a value of 0. Hydrogen, even though hydrogen is not present in the elemental form, because in the most stable state, it is always present as a hydrogen gas. Okay, so that is given a value 0. If you talk about hydrogen in the monoatomic state, that will have a positive value because that is less stable compared to H2 gas. Same thing with nitrogen. Nitrogen in the most stable form, which is with the gaseous form, at 1 atmospheric pressure and 25 degrees centigrade, that is given value of 0. If you are talking about monatomic nitrogen atom, that is less stable than N2 gas, so that will be given a positive value. Same thing for oxygen gas also. So let's look at water. Okay, so water at 1 atmospheric pressure and 25 degrees centigrade, it will be in the liquid form. Okay, so this quantity for water is this quantity. Okay, so supposing you want water, let's say enthalpy of water at 2 atmospheric pressure and let's say 800 degrees centigrade. Okay, so for doing that, so you take this quantity, which is this quantity, and then this quantity refers to gas phase water. Okay, so gas phase water, that will be water vapor. So the difference between this quantity and this quantity is the enthalpy of vaporization, standard enthalpy of vaporization. Okay, that is, you have taken water from liquid state to the vapor state. Both are at same temperature and pressure. How do you do this? Okay, so the way to do this, there are using statistical mechanics, there are lots of models. In fact, many of the things that are computed now, if you want the values, they are computed from models of statistical mechanics, but you can also make measurements. Okay, so the traditional way, let's say 50, 60 years ago, the traditional way of measuring these quantities was using experiments, but now very accurate computation models using statistical mechanics and quantum chemical models is available to compute all these quantities. Okay, just to re-emphasize, this quantity for water refers to this quantity. This quantity is this quantity. And then you take, let's say, water vapor from your reference temperature and pressure, which is 25 degrees centigrade and 1 atmospheric pressure, to the temperature and pressure of relevance. Okay? Here the phase is just one and the same. Here the pressure can be 2 atmosphere. This can be, let's say, 800 degrees centigrade. Okay, water is not decomposed at these temperatures. So that is the sensible enthalpy change with reference to water vapor at the standard reference state. Okay, so you should know what these three terms mean and where you get these quantities. Okay, so these are well tabulated in all your textbooks. So please go over the appendix. In different textbooks have different tables, but you go through them very carefully to understand how they are specified. So here we are only dealing with enthalpy. In the next lecture, we will look at these two quantities. Okay, or next lecture or two, we will look at these quantities, and we will also talk about this quantity in this lecture itself. So this is conceptually, this particular lecture is fairly simple, okay, because these things are you've learned from your high school, but how do you utilize it in practice? Where do you get these data in practice is the emphasis of this lecture. Okay, so please go through this carefully, and when you work out the problems, it will be more clear. Okay, so especially this part. Okay, how is this correlated? This part is correlated with the tabulated values. That's something which you have to know carefully. The rest of balances are fairly simple. If you're thinking about a flow process operating at steady state, you always just balance the energy, incoming energy and outgoing energy. Okay, this kind of balance we've done many, many times. There's nothing really novel here. Conceptually, it's not any more complex compared to all the balances which you've done in the past, except that how do you think about enthalpy changes involved in reactions. Okay, so there is again there is incoming quantities. There is net rate of heat transfer, net rate of work transfer. We have not implemented the sign convention yet, and then there are reactants coming in at a particular rate that's indicated by this quantity, and then the enthalpy of the incoming reactants is specified using the procedure which we just discussed in the previous slide. And then it is balanced by the outgoing energy changes. Right? And instead of measuring per unit time, indicating all these things per unit time, you can also not specify using rate measures, but you can just talk in terms of energy transfer. And now we have implemented the sign convention, right? The typical sign convention that you use for heat transfer and work transfer. So this is the standard energy balance, which you've seen in many of your previous lectures. And then there are different ways of specifying per unit mole, per unit mass, and so on. These are not conceptually complex. I'm not going to elaborate, just work out some problems to get a better understanding of this point. So there is another terminology, jargon, which you should be aware of. So there are two ways to specify heating value. Okay, so what do you mean by that? When there's combustion, there is heat that is being released. The heat that is being released is specified by either lower heating value or higher heating value. For example, so let's say the product of combustion, supposing you combust hydrogen as a fuel. Okay, so the product of combustion is just H2O. There is no carbon involved. So there is 1 kg of hydrogen, let's say, combusted with air, and you get H2O. The H2O that is being formed can be in the form of a vapor or in the form of liquid water, right? So these two quantities are different, right? So if supposing you release vapor, the heat transfer involved in such a process when the product is in the form of water vapor is called lower heating value. Why? Because when supposing you cool down this water vapor to liquid water, new bonds are formed, hydrogen bonds are formed, that would involve some more heat release, right? So your heating value is higher when the products are in the liquid form, okay, compared to products being in the vapor form. And the difference between them is the enthalpy of vaporization, right? So this is enthalpy of fusion or enthalpy of vaporization, difference between enthalpy of vapor and enthalpy of liquid, and this depends upon the mass of products that are being formed. And then there's another jargon that is typically very useful, adiabatic flame temperature. In this case, there is no heat transfer to the environment. All the combustion, the heat that is released due to combustion is being utilized for raising the temperature of the products. Okay, so this is the maximum temperature to which the products can be raised to, right? Because there is no work transfer, there's no heat transfer to the environment. So all the heat released is utilized for increasing the temperature of the products. So the temperature of the products is at the maximum level. Well, none of the heat is escapes out to the environment, or no work is done on the environment. Okay, so that's called adiabatic flame temperature. That's the maximum temperature. This is usually not the case, because there will be some heat loss. So, and the temperature of the products that is released will be always less than the adiabatic flame temperature, because there can be some heat loss, the combustion might not be complete, and there can be dissociation of the product. There can be bond breaking of some of the products. All these will make the temperature of the products less than the adiabatic, the maximum temperature that can be obtained from the combustion. So the heat released in combustion depends upon the ratio of, let's say, air to fuel. Okay, it may not be exactly stoichiometric. Many times you may use excess air, in which case much of heat is used for raising the temperature of air. Okay, or supposing it is less than stoichiometric, that is, you do not use enough air to combust all the fuel, then there can be incomplete combustion. So there are many reasons. Here we have mentioned 3 of them. Because of these 3 reasons, the temperature of the products is less than the maximum temperature that is possible. Then for a closed system, things are even more simple. That is, there's no incoming and outgoing, incoming reactants and outgoing reactants. So you just have some fuel and oxidant in a container, and then there can be heat and work transfer, but there is no incoming and outgoing products. There are no incoming reactants and outgoing products. So everything is a closed system, even though there can be heat transfer and work transfer, heat interaction, the work interaction between your system and the environment. So it's just the first law, energy balance here, which we've done many times over. So you use the relationship between internal energy and enthalpy to specify internal energy. Okay, why? Because so all the, with respect to chemically reacting system, all the tables will specify enthalpy. Okay, so using the relationship between U and H, we can get the values of U, because this is what is being in standard table. This is what is available to you. All the rest are fairly similar. You just plug in U in terms of these quantities and then present the formula. This is a computational formula that you utilize for getting, for making the first law of balance for a closed system. All these things are to be seen in the context of the broader question of energy. In the broader question of energy, energy density is a very, very important issue. Okay. So here, how much of energy is released per unit volume of the fuel which you are talking about, or per unit mass of the fuel you are talking about. So if you look at what has been traditionally used, okay, so let's say natural gas and so on, they're not only easily available, okay, their energy density is very large. Okay, so if you compare to batteries, even though batteries can be charged from renewable energy, the challenge in batteries is that their energy density is quite low. Okay, so that's why it is not so easy to run your car using batteries. Okay, if you have an electric car, 50% of the weight of the car, almost 50% goes into the weight of the batteries that are being utilized to run the car. Okay, as opposed to that, petrol and so on, they have very high energy density. The cleanest of fuel, okay, is chemical fuel, is hydrogen gas. They have very high energy density per unit mass, but the challenge is that hydrogen is a gas. Okay, how do you store it is very difficult. It's a big challenge. Even though the energy density per unit mass of hydrogen is very high, per unit volume is not that, it's very low. Okay, it's almost like that of a battery. Okay, so there are pressurized hydrogen. If you make hydrogen into a liquid form, you are able to increase the energy per unit volume to greater extent, but these are all more challenging options. Okay, so this you should be able to. This is not a class on energy, but this is very important to understand these issues because this is thermodynamic in practice. Okay, thermodynamics in practice. So this is a slide that this is a graph that I got from Wikipedia. At least you go and appreciate this graph because this is a very important consequence how people are trying to improve use fuels with higher energy density or how to improve the energy density of non-polluting fuels. Okay, let's say hydrogen is a non-polluting fuel, but it has its own challenges. So all these are the issues that will be addressed in the next 20, 30 years. So as students, you should have a good appreciation of these questions. With this, I'll stop here. We will look at entropy changes and free energy changes associated with chemically reacting system in the next couple of lectures.